Let us now discuss a special case of combined stresses, which is called kern of a section. The kern of a section is the region in which a compressive point load may be applied without producing any tensile stress on the cross section. So for example, if we have this cross section, which is rectangular, having length L and width B, the kern of a section is a region where we can apply a compressive load without causing tension in any point within this cross section. This can be explained by this another example where we have got a masonry pier subjected to some concentrated loading. The concentrated loading is eccentrically applied on this masonry pier. In other words, the concentrated load is at a distance x from the y-axis and at a distance y from the x-axis. Thus, we would have a case of combined stresses consisting of compressive stress P by A and two flexure stresses due to the moments about x-axis and moment about y-axis. We can see that compressive stress is the same in all the four quadrants, which will be equal to P by A. It is the difference in the flexure stresses which will cause different combined stress in each and every quadrant. So for example, in the second quadrant, we would have the compressive load P by A and the flexure stress about x-axis compressive and the flexure stress about y-axis negative. In the third quadrant, again, we would have a compressive stress P by A and the flexure stress about x-axis tensile and flexure stress about y-axis tensile again. In the case of fourth quadrant, we would have the compressive stress P by A and the flexure stress about x-axis tensile and the flexure stress about y-axis compressive. So the main idea of the kern of a section is finding out a region in which the compressive point load may be applied anywhere without producing any tensile stress on the cross section. Now this is true in the case of this masonry pier, as masonry is very weak in tension. Later we will see that actually the kern in the case of this rectangular section would be a diamond shape. Thus, if we apply the load inside this diamond shape, regardless of the load being in any quadrant, we wouldn't have any tension appearing within the cross section. Please note that in this scenario where the concentrated load is applied in the first quadrant, we have the third quadrant tensile stresses developing. The reason is that we would have a compressive load P by A only applied and the flexure stresses about both x and y axes are tensile. Thus, one thing we can appreciate that the quadrant which is diagonally opposite to the load application would have tendency of having tensile stresses. We will now try to derive an expression for that eccentricity E, which will ensure no tensile stress is developed within the cross section. We'll first do it for a 1D problem and then carry over the concept to the 2D problem. So in this figure, we have a short strut carrying compressive load P applied with an eccentricity E along one of the principal axes. The addition of a pair of forces P1 and P2, each of magnitude P and acting at the centroid of the cross section, causes the equivalent loading shown in this figure. In other words, the load P can be transferred via force couple system to the centroid by adding the load P1 and P2 at the centroid. Thus, the two opposite P will cause a couple, and we would have the load in the same direction as P remaining. Hence, we have the load P and PE being transferred to the centroid of the cross section. Now, we can appreciate that this is a problem of a combined stresses because we have got an axial load and a moment applied on the cross section. The stresses across any typical section Mn are the results of the superposition of the direct compressive stresses. Thus, sigma A is equal to P by A is the compressive stress, and sigma F is equal to P times E times C over I is the flexure stress. P times E is the moment, C is the distance of the extreme fiber from the centroid, I is the moment of inertia of the cross section. If the maximum flexure stress is larger than the direct compressive stress, the resultant stress appears as in the figure E. So the axial stress and the flexure stress is, so the axial stress and the flexure stress are added up to give the resultant stress shown over here. Please note, because of compression at the right hand side of the cross section, we have the flexure and the axial stress adding up. Whereas on the left hand side, we have axial stress getting subtracted from the flexure stress because of opposite directions of the axial and the flexure stresses. After summing up the axial and the flexure stresses, we would realize that the neutral axis of the cross section has shifted. This shift is equal to A from the centroid of the cross section. This figure shows the new location of the neutral axis. The point of zero stress, which is the new location of the neutral axis, can be easily found by computing the distance A at which the tensile flexure stress equals the direct compressive stress. So, in the light of our previous discussion, the combined stress formula is plus minus P by A plus minus My or I if the stresses types are axial and flexure. In our case, if we take compression as negative, then we can write sigma is equal to minus P by A plus My over I. At the point of zero stress, A, we have sigma equal to 0, and that will make P by A equal to Ny over I, plugging the value of M, which is Pe, and Y, which is A, we will get Pe A times I, where A can be worked out as equal to I over capital A E. I is the moment of inertia, A is the cross-sectional area, and E is the eccentricity of the loading. It is evident that there will be no tensile stresses anywhere over the cross-section if the direct compressive stress equals or exceeds the maximum flexure stress. Thus, for a rectangular cross-section having width B and height h with P applied at any eccentricity E, we can write P by A is equal to MC over I is equal to PE times h by 2 divided by B h cubed by 12. C is put as h by 2 because we are interested in that eccentricity E, which will at the most move A to the extreme end. The point of zero stress moves to the extreme end, then that would mean that the whole cross section is under compression. Therefore, A is plugged in as h by 2. from this we can get the maximum eccentricity equal to h by 6. Thus, if the load lies within h by 6 of the centroidal axis along the principal x direction would ensure that no tension develop in the cross section. This expression is the basis of well-known rule that in designing a masonry or other structures weak in tension, the resultant load should fall in the middle third of the section. We shall now consider the general case in which the load P is applied at any point with respect to the principal x and y axes. Considering Ex and Ey represent the eccentricity of P with respect to the x and y axes respectively. The moments of P with respect to x and y would be Pey and Pex respectively. Thus, by superposition, we can write now our sigma equal to minus P by A minus P times Ex into x over Iy minus P times Ey into y divided by Ix. In this general case, we have the compressive stress whose contribution is shown in our combined stress equation. Then we have the moment about the x-axis, or in other words, the flexure stress about the x-axis whose contribution is shown by the second term. And we have finally the contribution of the flexure stress about y-axis shown or captured by the third term. Similar to the previous case, we can again put sigma equal to 0 and simplify this equation. We can also plug the value of moment of inertia equal to area times radius, square of radius of gyration. Thus, Iy equal to a ry square and Ix would be equal to a rx square. This will give us the equation of straight line shown as 1 plus Ex by r square y times x plus Ey by r square x times y equal to 0, where we can define the intercepts as u equal to minus r square y by Ex and intercept v equal to minus r square x by Ey. In this general case, the neutral axis passes through the quadrant that is opposite to the quadrant containing the load P. This we discussed right in the beginning by stating this example of masonry pier. Thus, if the load is applied in the first quadrant, we would have a compressive stresses due to axial load P getting added to the tensile flexure stresses caused by the moment about x and y axes. It is due to this reason that the quadrant opposite to the applied load P will be subject to some tensile loading. In order to ensure that the full cross section is under compression, we will have to apply the load at such eccentricity that this neutral axis is at most moved to point B as shown in this figure C. So in this combined stress equation, if we put sigma equal to 0, x is equal to minus h by 2 and y is equal to minus b by 2, we will get 0 is equal to minus P by BH plus P times EX times H by 2 divided by BH cube by 12 plus PEY times B by 2 divided by HB cube by 12. And from here, we will get EX by H by X 6 plus EY by B by 6 equal to 1. The terms in denominators are the x and y intercepts of the straight line respectively. So this equation is the equation of straight line about Mn, bearing in mind that the load is applied in the first quadrant. This line intersects the x-axis at h by 6 and the y-axis at b by 6. Similarly, we can apply the load in the second, third, and fourth quadrant, and we will get a locus of points. And placing the load inside this region will ensure that no tensile stress is developed within the cross-section. In the case where the load P is applied in the first quadrant, moving outside the locus of the points shown in red would develop tensile stresses in the fourth quadrant. However, if the applied load stays inside this red region, then we would have the whole cross-section under compression. At point B, we would have stress equal to 0 if our applied load P is at the extreme boundary of this red region. The same argument can be applied if we have the load P applied in the second quadrant. Here we will have to ensure that the load remains in this green region in order to produce compression in the whole cross-section. If the load is at the boundary of the green region, in other words, along the line M1 and 1, then we would have zero stress developing at point C. Continuing this procedure indicates that evidently no corner and no part of the cross-section will be in tension if the resultant compressive load lies on or within the diamond-shaped figure. This shaded area is known as the kern of the cross-section. We will now discuss some examples to reinforce the concept of kern of a cross-section. In this example, we have got a rectangular section having width 0.4 meter and depth 0.8 meter. It has got a concentrated load applied at one of the corners. The vertical concentrated load is of 40 kilonewton. We are asked to determine the largest normal stress acting on the section through A, B, C, D. As we have discussed, the largest compressive stress will be in the quadrant where this concentrated load is applied, and the minimum combined stress will be in the quadrant opposite where load is applied. Thus, we can write the normal stress equal to P by A, so 40 kilonewton by 0.8 by 0.4 will give us 125 kilopascals. Due to the moment about x-axis, we have 8 kilonewton meter times the distance of the extreme fiber, which is 0.2 meter, divided by moment of inertia about the x-axis, which is 0.8 times 0.4 cubed by 12, and that will give us 375 kilopascals. Similarly, the flexure stress about the y-axis would be equal to my cx over iy. My is 16 kilonewton meter times 0.4 meter divided by 0.4 into 0.8 cube by 12, which will give us again 375 kilopascals. Please note that the moments 8 kilonewton meter and 16 kilonewton meters are determined by multiplying 40 with 0.2 meter and 40 with 0.4 meter respectively. So 40 times 0.2 will give us 8 kilonewton meter and 40 times 0.4 will give us 16 kilonewton meter. All these three can be added to get the combined stresses. Adding them up will give us minus 875 kilopascals for the first quadrant. Now let us look into this other example which was discussed in the beginning of the lecture. So we have got a masonry pier that is subjected to 800 kilonewton load applied in the first quadrant. If x is equal to 0.25 meter and y is equal to 0.5 meter, determine the normal stresses at each corner A, B, C, D and plot the stress distribution over the cross-section. Neglect the weight of the pier. Again, this is the problem of general combined stresses. We have got the 800 kilonewton load causing axial stresses and flexure stresses within the cross section. So using our combined stress equation, sigma is equal to P by A plus mxy over Ix plus myx over Iy, and plugging the values in this equation will give us stresses at the corners of the masonry piers. So area of the cross section is equal to 3 times 4.5, which is 13.5 meters squared. The moment of inertia above the x-axis is b h cube by 12. In other words, 3 times 4.5 cube by 12, and that gives us 22.78 meter 4. The moment of inertia about the y-axis will be equal to 4.5 times 3 cube by 12, and that will give us 10.125 meter 4. Now, bearing in mind that compression is taken as negative, in the combined equation we have mx and my, which can be determined as follows. Mx is equal to 800 times 0.5, which is 400 into 10 raised to power 3 Newton meter. My, on the other hand, is equal to 800 into 0.25, which is equal to 200 into 10 raised to power 3 Newton meter. After finding out the moments about x and y axes, we are now in a better position to use our combined stress equation. This combined stress equation is the same which we derived previously. So in this equation, we have got sigma equal to minus P by A minus mxy over Ix minus myx over Iy. This equation is written with respect to the quadrant where the concentrated load is applied. Now, in order to find out the stress at A, we have to use x equal to minus 1.5 meter and y equal to minus 2.25 meter. Hence, we get the second and the third terms positive. So plugging the values, we get minus 800 into 10 raised to power 3 divided by 13.5 plus 400 into 10 raised to power 3 times 2.25 divided by 22.78125 plus 200 into 10 raised to power 3 into 1.5 divided by 10.125. 800 is the applied load, 13.5 is the area which we determined, 400 10 raised to power 3 and 200 10 raised to power 3 are the moments, mx and my respectively. Ix is 22.78, Iy is 10.125, and y and x are minus 2.25 and minus 1.5 for the stress at corner A. And that will give us 9.88 kilopascals in tension. Similarly, we can find the combined stress at point B by plugging the values in the same equation and making the corresponding use of y and x. In other words, the variables in this equation will stay the same. It is only the values of y and x whose sense would determine which corner stress we are interested in. In the case of sigma b, we have the value of x equal to plus 1.5 and value of y equal to minus 2.25. Hence, negative comes with the third term and positive comes with the second term. Sigma b would be 49.4 kilopascals, and that would be in compression. Sigma c would have x positive 1.5 and y positive 2.25. Hence, both the second and third term will be added, and we would have the maximum compressive stress of 128 kilopascals developing in the first quadrant. Finally, sigma D would have y equal to plus 2.25 and x equal to minus 1.5, and that will give us 69.1 kilopascals in compression. Please note that we are asked to neglect the weight of the pier. The combined stress profile is shown in this figure. It is clear that the corner B, C, and D are in compression, where the corner A is in tension.